get at least one point connected is going to 1. Then I used square root trick to show that this probability goes to 1, and then I selected large n, that probability that you get a point from left, right, top or bottom connected is larger or equal than 7/8. And I'm doing this just because to guarantee of relatively large probability of some negative event, which I'm going to look afterwards. So now let us look at dual lattice now and just repeat the same trick which we were doing. So dual lattice. So dual lattice now I will denote in the same way as in Grimet's book, T and D. It's just part of dual lattice. So are points x plus half half. So it's essentially lattice shifted by vector half half. So if we had our original lattice in this way, so I believe everyone is already familiar. So I produce at the center of plaquettes of original lattice new vertices, and they are connected by bonds. So you immediately see that dual lattice is just isomorphic to original lattice. Maybe I should put colors. Dual bonds. And again, as we did yesterday, I will say that dual bond is open when original bond perpendicular is closed. Okay? And now again, you see that dual bond is open because we are working on probability 1/2. So for dual bonds to be open or closed, we have the same probabilities half-half. So we have just the same model on dual. And then I can ask now, for the same sequence of questions, you just shift this box, which was originally, say, we can think of it as built at the positive quadrant. So this box 0, 0, this is n, n. And then if I look at dual box, it's going to be shifted by half. I'm not going to draw a detailed picture of this. So we have dual box. And at this dual box, we are asking the same questions of probability for event AU, where U is left, right, top, bottom, to be happening. And of course, you just need to put that everything is happening on dual lattice, so immediately we can reach conclusion that probability that A U of n with subindex D happen is also bigger or equal than 7/8, right? So this means that we have now, if this event occurs with subindex D, it means that you are looking at dual lattice and you are asking now for existence of vertex on dual lattice. So now it's one vertex would be inside of original box, such that you have an open path from one of these vertices to some other vertex, right? And this is on dual lattice, which implies that somehow, if you now switch from looking at dual lattice to the original lattice, you will have sequence of closed edges which are moving from this vertex to plus infinity. And of course, this sequence of edges which are closed, which are producing paths on dual lattice, they are not producing a path in usual way on original lattice of closed edges, but they're producing sort of fence, like, you see what I mean? If this is closed, it's a dual path, and then it moves, means this was closed, maybe it moves upwards, this was closed. So following dual paths, you can produce, in principle, a fence of closed edges on original graph, which separates something from one side to another side. So somehow dual path really separates pieces. And then you have the same probabilities for these events to occur. So that would very important that we are sitting and looking at these things at dual. So work essentially is done, because now you look for the following event to happen. It's a new A. New A. It's I want that exists a path starting on original lattice from vertex on the left boundary to plus infinity. So I'm looking for event ALN, and I'm going to look at intersection. I want at the same time to occur A right n. Then I want something different than from our original picture. I want that happens A top bottom dual lattice n, and intersection with A bottom on dual lattice n. So I'm looking at this event. So if we now again make this picture anew, essentially what I'm asking to have a path from some vertex here to some vertex here on the left, and from some vertex on the dual which is here, and some vertex on the dual which is here. So this is what is our A. Okay, and let us look at complementary now of this event. So probability, once everything is done at half of A complement, so I'm looking at this doesn't happen. It's smaller or equal than probability at half that event AL doesn't happen. And in fact now I'm working at the scale, at the size of event of capital N, which guarantees to me that some probabilities are bigger than 7/8. So in fact, let me define it like this. So I'm changing capital N, capital N. So AL N doesn't occur, right? Plus at half the same story with right, so complement of right doesn't occur, plus probability at half that on dual I have problems on the top and on the bottom. And now, so there's last term for the bottom, a bottom of N D. And now I had this condition, right? So now probability of complement of each of these events on dual and on the original lattice is smaller than 1/8. So this probability is smaller than half, right? Probability of this event to happen. So which means probability of straight event to happen is bigger than half. So it's strictly positive. But now here comes contradiction. So this event has positive probability to occur. Okay? But if this event occurs, you may ask yourself, but what happens inside? And inside you have not much choice. Inside is going to be the following. Either this is connected, either this is connected. Right? You have no third possibility because we are on the planar graph. So they cannot occur both. If you were in higher dimension, they could go around each other and connect. But if, so you see, because we are using now planar duality of the two, either these two red are connected, either these two white are connected. Okay. Now, what happens, what's wrong with that if they are connected? If, suppose that this is connected to this in some way, so it could be inside, it could be connection very complicated actually. So, but if this white, so let me put C1, is connected to this branch C2, means that these two red cannot be connected. Because this piece is infinite. We assume that this part, starting from this point, goes to infinity. You potentially do not know how it goes to infinity. But this also goes to infinity, and you knew that they don't use vertices from the box. That was condition. At the same time, you knew that there is path crossing dual paths going to infinity and dual paths going to infinity. So this guarantees, just because we are in dimension 2, that couldn't happen that this path, which you started here, goes to infinity because it comes here, touches this, and goes to infinity. This cannot happen outside of this box because these two fences protecting. You cannot go around. If you want to go, you go only through the box. You agree? But if you go through the box, means that immediately that's geometric exercise, that you have double infinite path, wide, which goes from infinity to infinity. And this double infinite path separates this part, which is red, and this part, which is red, right? But what's wrong with this? And Menshikov theorem tells us, now uniqueness of the cluster. So if you now look, if suppose this is happening, and this is happening with positive probability, but this implies now you go back to dual lattice, which is isomorphic to your original lattice, and you discover that with positive probability you have two infinite clusters. But we just proved a few minutes ago that two infinite clusters, disjoint infinite clusters, have probability 0 to appear. So this cannot happen, right? In the same way, if this is connected by chance, that means that you have two infinite open clusters at original lattice with positive probability, which also is contradiction. So only part where we could assume something wrong, part is here, that you have an infinite open cluster. So this assumption is wrong, which implies that theta or half equals to 0, and as a consequence, we get that PC is bigger or equal than half. Okay? So it's very planar trick, but still it's very elegant and short proof, actually. It's trivial. Provided you know very sophisticated theorem that unique infinite cluster is unique. Without this theorem, this argument doesn't fly. Okay. So we proved this, and now my goal is to show that PC equals 1/2. So if I show that PC equals 1/2, I already because of this statement, I would have this theorem that theta of PC of Z2 equals to 0. So now, in order to prove that PC equals 1/2, unique thing which you want to show, that to convince yourself that PC has to be smaller or equal than half, then it would imply that PC exactly half. Okay. So this argument, which I'm going to now do, it's also nearly trivial, and in some ideological level, it goes back to Russo-Seymour-Welsh arguments. So, again, of course, duality will be employed in a very substantial way. So let us prove another lemma. Lemma 2, let us call it first one lemma 1 of today. Lemma 2, PC of Z2 bond percolation is smaller or equal than half. Okay, so how we move in this direction, and in some sense, proof is also similar to what we did before. So let me make it short somehow. So because of planar duality of Z2, in order to have something blocking, you know, if you have some structure, open structure on original lattice open, in order to block, you need to have contour on dual lattice, which is contour of open edges on dual, which means you have sequence of closed edges on original lattice surrounding my open cluster. So I will use this fact, and then my goal is to show that if P is smaller than PC, I would like to conclude that 1 minus P is strictly larger than PC of dual lattice. So if you take subcritical value of P on original lattice, then in our case 1 minus P will be supercritical for dual lattice, but now dual lattice is just the same lattice. So PC of dual lattice is just the same PC, so I can drop now this dual lattice, and then if I succeed to do that, it immediately implies that PC equals half. Because I already have that PC is bigger or equal than half. So how do I do that? So take now original lattice and look for the following event. I take some vertex on negative part of x-axis. I fix some number, just to be consistent, fix some number m positive, being large, so here is m. And I will be asking for the following event to occur, that there is an open path going from some vertex which is on the left to 0 to some vertex which is to the right of m. So I'm looking for the event that there is connection, and more than that, I will ask that this connection lies entirely in upper half or entirely in lower half of the plane. Okay? So I'm looking not for some path, but I'm looking for the path of this type. Okay? So, and here I'm leaving untouched. So I'm not considering path of this type that starts here, goes through this gap between 0 and m, and touches here. So if I want to have these two pieces connected, negative part of the plane and half part of the plane starting from m, I want them be lying in one half of planes. Okay, so this is event AM. So let me divide it more properly. AM exists an open path D, which originates at some vertex let me use notation from the book, K0, with K being negative, vertex at some vertex and ending at some vertex L0 with L bigger or equal than M. So just formally wrote what I said. But now remember what we did yesterday. We proved Menshikoff's theorem, and Menshikoff's theorem said us that once you take P below PC, open size of the open cluster, diameter of open cluster, decays exponentially fast. Or in other words, proof of Menshikov implied yesterday that PT equals to PC for large, well, yesterday we proved it actually for ZD. And now what I'm asking here, that exists a path moving from some vertex here to some vertex here. So think for a second that this is large gap. So this distance should be, probability to have such a path is going to be decreasing exponentially fast just because of Menshikoff's theorem. So one of consequences which we will use, that expected value of cluster of the origin, which is now just C equals bigger or equal than N. N runs from 1 up to infinity. is finite. So you see, because I am below PC, I already not adding C being equal to infinity because it has probability 0. So this series is finite. Then probability of event AM to occur, I'm going to think of M being relatively large. Then, of course, it's smaller or equal than probability under P of union, where L runs from M up to infinity of events point L0 is connected to point K0 for some K negative. Do you agree? Okay, but that's essentially it, because what I get, this is smaller or equal than probability under P that's cluster has size bigger or equal than L, and when L runs now from M up to infinity, but now observe, this was finite, so when you push M to infinity, this quantity you can make as small as you wish, right? Now means that probability of this event, if you are below PC, you can make as large, as small as you wish, pushing M to infinity. So now to complete the proof, let us look at event. If I look at this line, so there is origin, and there is a piece of line up to M, and you just by force take and open all edges here, and look at connected component of this segment on dual lattice. Okay, so we are looking now, we are switching to image, let me put it red. Let me put it red. So I'm looking at open connected component on the dual lattice. So there is some cluster which is moving around. Etc. And now we want to know, is this object, when M goes to infinity, has chance to be infinite or not? And if it does infinite, it immediately implies that 1 minus P, because now edge is open on red graph, which is dual, is 1 minus P, is supercritical if it's infinite. So, but this guy is infinite if you have no contour. So let us put what is happening if this object is finite. If the object is finite because of planar duality, then you need to have a contour which surrounds this object. But we just proved that this sum is finite. So in principle, if this fails, I can take even larger M and try it again, still on the same configuration. I just erase what I knew. So you will have only finitely many possibilities just because of Borel-Cantelli to bound this cluster from being finite. So this immediately implies, this was we got here, that with probability 1 for M large, if you take M large, this cluster will be infinite, because you will be not able infinitely many times bound this by closed arc. Is that clear or not? So complete the argument. It's essentially all here. So it immediately, if you believe what I just said, so it means that probability that you get red infinite component is 1, and immediately implies that 1 minus P is strictly larger than PC. And this immediately implies that PC equals 1/2. Is it clear? Some questions? Okay, so what we have achieved by now, so we saw that theta of PC equals to 0. So the rest of the class now I will show how which alternative methods could be applied to try to tackle this problem for higher dimensions. So in particular for 3, 4, and 5. So let me introduce now another process. So there will be a bunch of problems to think for the weekend. So all now goal is to think about what can we say about theta of PC, and think that we are discussing now issue of ZD, D equals 2, 3, etc. Okay. So one possible way, alternative way, it's a very beautiful mathematical construction, is to think about invasion percolation. And let me explain how this model works, and then how it is related to original side or bond percolation. So as a model, invasion percolation is relatively simple. So let me draw informally a two-dimensional picture of this process. So the best way of thinking of it is sort of like dynamical procedure. So here is origin. And assume now that with every edge of your graph, so here is Z2 and you should think about Z3, etc. With every edge, I will associate random variable psi e, which is, for example, either exponential with parameter 1, or you can think of uniform between 0, 1. It doesn't really matter for definition of model. So maybe I prefer to stay with uniforms, for example. So, but model is well defined for any other. So it will be convenient for some other purposes. So now, at each edge, instead of talking of being open or closed, I simply just put uniform random variable. Is that clear? So we have now new configuration of our model. Is just realization of this x's. So you have a number attached to each edge on your picture, and this number is chosen uniformly, picking in between 0 and 1. Now, how invasion procedure works? So it's sort of dynamical definition of the random graph. It's random tree, actually. And let me do it in informal way. So at the beginning, who belongs to this random tree? So let me denote by gamma K, invasion graph, invasion tree, after K steps. So I will now show how you construct this tree. So you start that gamma after 0 steps contains only one vertex, which is origin. So you start from the origin, and name of the process speaks for itself. You look at 4 edges, which you can invade, which means adjacent edges. So let me denote E1, E2, E3, E4. And now configuration is fixed. So you are doing, in some sense, if I can say informally, unquenched realization of your x's. So you now have 4 values: xi E1, xi E2, xi E3, and xi E4. And now look at smallest value. You take minimum of this. So you take minimum of these 4. This is, in some sense, weakest edge which you see, And then what you do, you simply invade this weakest edge and add new vertex to your invaded territory. So now you are owning at step 1 two vertices, origin and vertex which you conquered by invading weakest edge, right? Now you want to expand. So now both vertices are active. So now you look at all edges adjacent to your red region, which you could invade. So these edges, you already know their values. They're staying at these positions, but now you can try another. So it would be E5, E6, and E7. Now what you can do, you look at minimum over all of them. So now you are looking at Xi, say, E1. Xi E2 was taken because it was minimum among these three. So, but still, Xi E3 is around, Xi E4 is around. Then you got extra, Xi E5, etc. And then we have Xi E7. And again, take minimum of this and invade. So minimum could be any of these 6. It could happen that at the first step this was smallest, but now E1 is smallest, or could be E7 smallest. So you choose smallest one and you invade. So you keep doing this procedure. So at next step, for example, this could be invaded, this could be invaded, this could be invaded. And also you admit the following rule, that if this eventually is invaded, right, then this edge you don't care to check, because anyway these 2 points are already added to your invasion cluster, so there is no point to put edge here, because if this is at given step of procedure is already checked, and if you choose as minimum, it simply doesn't add new point to your universe, because you already are owning these 2 points, right? So what you see, according, if you follow this rule, you are producing random tree, and this random tree is growing in space. Okay, so without going into formalities, now I believe, I hope it's clear what means for you gamma n. So it's what you see after n steps. So second observation is it clear that this procedure never stops? Because if you made n steps, then you have all possible edges which are adjacent to red tree. You always have places where you can expand, and then your next step will be just picking smallest one. So this procedure is infinite. So finally, this gamma n is growing, so it's clearly that gamma n is a subset of gamma n plus 1. And finally, you can think about limiting object, which is gamma infinity. So this object gamma infinity is a tree on your lattice, and this tree not necessarily is picking all points. So is gamma n, in fact, is much smaller. Is leaving a lot of things behind it. So it's moving away. Is this object clear? Okay. So this is invasion 3. Now, exercise. It is sophisticated exercise. One side is simple, one direction, another not. Now, this exercise postulates connection between invasion trees and our original model. So you see, this model, it's a beautiful mathematical object to study, and in fact, I must say, very little is known. It's a very difficult object. It's a stochastic structure in space, which we know very little about its behavior. But now the following is equivalent. Theta at PC. And then I would write, if you wish it makes things easier to think, of ZD, theta of PC of ZD equals to 0, is equivalent that probability. So now I didn't define formally probability for this model, but I hope you understand what I mean. probability that X belongs to infinite, it's captured, somehow it's captured by invasion graph, goes to 0 if X norm goes to 0, goes to infinity, sorry. So you see what is written? Probability to have infinite cluster at criticality on ZD is equivalent to the fact that invasion percolation doesn't essentially catch point if this point is far away. So you see this object is growing, and then a priori, if you didn't think about this model before, it's not very obvious to you, I believe, how is geometry of this pink cluster. It's sort of think very voluminous, or it's finding its kind of very easy way somehow in valleys of low values of eta, and somehow, if I could say, if looking from far, it looks like to you nearly one-dimensional paths trying to escape by easiest possible mean. Okay, so but observe the following. If you think about dimension 2, of course, dimension 2 is not interesting for us because in dimension 2 we just proved that theta of PC equals to 0. But arguments suggest you something to think, and it's really beautiful open problem to solve. So if you are in dimension 2, so I'm going to rely on planarity of somehow my argument, but in fact you can stretch it to higher dimension. So, and now look at invasion on Z2. Okay, so what can you conclude? So at the beginning your life is a little bit chaotic, you don't know what exactly happens, but if you look at these random variables psi e, which are now uniform, right? Uniform in 0, 1. You look at those variables which have values not very much different from values of PC. So fixed number P, which is PC plus some delta, and think of this delta as being very small. Okay, so you're just above PC slightly. Okay, so and I'm looking now at random variables psi e such that psi e is smaller or equal than this p delta which is chosen. Right? What is probability of such random variable to be at given edge? Probability that random variable xi has this value is exactly p, right? So if my p is slightly supercritical, so each edge now at which I am looking, I can interpret as if it's open. So if you look at given edge and you assume that xi is smaller than your chosen p delta, you say that this edge is open. It's just new definition of being open. Okay? So, but now it means that each edge is open with probability slightly larger than PC. So if each edge is open with probability slightly larger than PC, means you have infinite cluster of these edges, open edges. And let me call them delta open, just because it's characterized by this parameter delta. So I have delta open cluster. You agree? So you have infinite delta open cluster, and now you need to somehow trust about geometry of infinite open cluster, which I was telling in first part. So this infinite open cluster is some structure in the space, which you do not know much where it stays, but you know that if you look at this image, means that microscopically, if you look at these edges around, all of them had values being smaller or equal than PC plus delta. All of them, just by default. And everything what is not on this cluster had values bigger than this. Correct? So everything what is not on the cluster, what is not white on this picture, if you take edge here which is not white, then means that value of this edge was bigger than PC plus delta. Is that clear? So if you look at this infinite cluster now, delta open cluster means that this delta open cluster has its outer boundary, which are edges which are all delta close. And this is true for all this picture. Now, suppose you start invasion from your origin, and origin now is blue here, and your invasion cluster is growing. You start to examine edges, something is good, something is bad, then you are moving. But now, because of planarity, if the origin didn't belong this delta open cluster, anyway it has to meet it, because it has to go out. There is no stop for this invasion. So it invades even edge. It could be surrounded by values very close to 1, is going to break one of these values, and eventually invasion cluster must traverse one of these delta close edges, because anyway life will be so bad that you choose smallest bad edge, and then we are sitting at the vertex which belongs infinite delta open cluster. Is that clear? You will hit delta open cluster. But once you hit delta open cluster, what I claim now, you never go out of it. Because once you hit delta open cluster, everything what is offered here, I am not knowing now, I don't claim I know where you will move, up or down. It depends on concrete value of these variables. But what I claim now, once you stepped on white, you will never go down from white. Just because whenever you go out from white, it's bigger value than white is offering to you. So your invasion cluster, whenever it reaches white, is going to continue on white, right? So invasion now actually is going to be spending its life on delta open cluster. But this delta actually was just not specified. So if you took delta, you can think about delta divided by 2 or delta divided by 20, etc. So what happens that if you think now about sequence of delta open clusters, you think about infinite sequence of delta n which goes to 0 from right. Okay? So it immediately implies to you that all these clusters, all of these delta n open clusters will be living on the previous one cluster. So if I took delta, for example, this white cluster, I could in the same way think about delta divided by 2 open cluster. So I claim delta divided by 2 open cluster, of course, is subset of delta cluster, just by default. It cannot be outside of delta cluster. Is it clear? It's just part. So if you think this is delta cluster, but delta divided by 2 is still supercritical. So delta divided by 2 open cluster is sub part of, so it takes some pieces of delta cluster. Is it clear? So if imagine that these are presented at colors, so I have white cluster, which is sort of dense fisherman net. Then I took delta divided by 2 cluster, which is subcluster of bigger cluster or more dense cluster, which is more rarefied. I took delta 3, which is decreasing to 0. And now I claim that once your invasion percolation starts to move and finds white cluster, it starts living on this white cluster until it finds yellow cluster. Whenever it finds yellow cluster, it never goes back to white cluster in the sense which is not yellow. It starts to move along yellow cluster. It starts to live, etc., until yellow cluster meets third color cluster, and you go down and you go down. And in some sense, this invasion percolation, because it never stops, it's somehow, if I could say, is jumping from one critical, supercritical cluster to another with decreasing value of its openness. In some sense, now we know that in dimension 2 we prove that there is no infinite cluster at criticality. But now you can imagine that moving along these structures in the space, this path is getting sort of more and more what I was mentioning, one-dimensional like. Yeah.
When you say that the process, the spatial percolation starts at the origin, fits the infinite cluster, you are using the geometry of the...
Yeah, for this argument, what we are doing now, just for simplicity. So now, just to answer your statement, if you are at ZD, right, in principle, if you have delta open cluster, my life could be going in between. So there is a statement. You will hit any delta open cluster with probability 1. It may take long time. I'm not knowing about first stage of your life, but with probability 1, just there are sophisticated theorems behind of this statement. So it's not completely for free to prove that invasion percolation in any dimension will hit any delta open cluster, right? So it depends on the fact that actually any delta open cluster has positive density, and then once you come close, it's a question of sort of local modification. That if, but I want to say, invasion will be moving in between cluster and eventually will be coming close to it. And then if you infinitely many times come close to delta open cluster, then eventually you will be invading it. So that's argument. But for this you need to know something. So, but in principle answer is like this. So, but where I want to arrive? So invasion, so you see, invasion somehow, invasion cluster is jumping from delta to smaller delta, delta prime, etc., etc., etc. All this process continues down, right? And now intuition is rather transparent. Now question is to prove this. So I believe over weekend you can do this exercise. So equivalence by itself is simple. What is difficult now to complete proof to show this part of the statement. That invasion, actually, if you start invasion from the origin and you fix point very far, so most likely invasion will go around this point without picking it. So probability that invasion hits your chosen point, if it's very far, it's going to 0. So this is very beautiful object, and also it was believed for a while. It's one of probably today most efficient concrete tool to attack this type of questions. So not so many techniques were created. So maybe if time allows, next week I will discuss a little bit about some renormalization arguments which were developed around mid-90s of last century, sort of block arguments to capture this fact that theta at PC equals to 0, and in some sense they had success, so people could do something in sort of oriented cases. But for general percolation process, I believe that invasion is still probably most promising tool to study invasion percolation. In fact, invasion percolation appears in many other contexts. So its process by itself is very rich, and it's very difficult process. So very little actually I can tell to you how this cluster behaves. Not so much is known. Okay, another problem which I like to tell you in the remaining few minutes. Some of you also maybe already heard, and it's also related to understanding structure of critical at criticality. So problem comes from Rob Vandenberg, the same Vandenberg in Vandenberg's Kesten BK inequality. And it's a very beautiful open problem which somehow relates what I was speaking before to what is going to be spoken in the next. So probably all these Loewner's stochastic Loewner's equation techniques might be promising for this problem. So look at the following process. So we take P being larger than PC. So, and graph at which I'm going to ask this question could be any your favorite graph. So could be, for example, ZD for any D larger or equal than 2. Okay. So if you take this P, which is bigger than PC of this lattice, say ZD, edge, bond, percolation. So you know that you will have almost surely infinite clusters somehow in space done. Okay. Now I'm going to start to formulate question. And question by itself not very simple, so let me do it more systematically. So first of all, fix delta positive, and for the future you should think that this delta is going to be very small parameter. Okay. Now I am going to do the following modification of configuration. So each configuration, percolation configuration, is going to be modified, in 2 steps. So how I do, let me describe it first informally, then I will write. At first step, you take this parameter P, which is supercritical, and you just throw Bernoulli configuration. So you see open and closed sides or open and closed edges. It doesn't matter. This model behind is not very relevant. So you have this configuration. So take Bernoulli configuration, this parameter P. So what you know, because P was chosen to be larger than PC, you have infinite open cluster. Okay. At step 2, you do something more drastic, and all edges, suppose we are in bond case, all open edges, let me do it, all open edges which belong to infinite open cluster are closed. So I'm doing something violent now. So I took configuration, and in my original configuration after step 1, I see open and closed edges. Among open edges, I suddenly discover open infinite cluster. So there are open edges which do not belong to infinite cluster, and there are open edges which do belong to infinite cluster. So open edges which do not belong to infinite cluster are now at step 2 left open. But every single edge which touches infinite open cluster now is closed. So you got new closed edges. So now when you look at procedure after step 2, again you see open and closed edges, but now you have new type of closed edges because originally they were open, but now you close them. But some of them are continue open, and you know if it is open, it is here, means that it didn't touch infinite cluster, original infinite cluster. Okay? So now, when this is done, there is a third step. So let me move here. Step 3. So let me put this as step 1, step 2, step 3. Now, in new configuration, after this yellow update, in new configuration, every closed edge is open. You give extra chance, is open with probability this delta. This probability delta. Okay? So now again you got new configuration. You had Bernoulli, you closed everything what belongs to infinite cluster. So infinite cluster, if you wish, was destroyed. And now you have closed edges, originally closed or closed because they were originally on the infinite cluster. And now, independently of nature, why they are closed, you give extra chance by delta. Okay? Question is, do you reconstruct infinite cluster? It could be different infinite open cluster. So you closed a lot of edges, but now you are opening a lot of edges. Okay? Now, can you, now question, for fixed delta, can you find P so close to PC that after all these 3 steps, I still can find an infinite open cluster? So why I'm saying, is the question clear, first of all? So for every fixed delta positive, can I or not find P, which is supercritical, such that making all these 3 steps, I still can reconstruct infinite open cluster? So let me tell you some obvious things. So suppose delta is very small. Of course, it's trivial to observe that if P is now extremely supercritical, think that P is close to 1. No? Everything is on infinite cluster. So once you throw this first, if P is almost 1, means everything is on infinite cluster, essentially. Then after step 2, essentially everything is closed, right? If essentially everything is closed, of course, there is no hope if your delta is very small to reconstruct infinite cluster, because if essentially all plane or space is closed at the step 2, if P is very close to 1, then no chance. Answer is negative. So, but once you start to push P to PC, now you can think about 2-dimensional case. So in 2 dimension, we know that theta of PC is 0. So function theta of PC is continuous at the origin. So which means that if you take P very close to the PC, theta of P is smaller than any epsilon you wish if you choose P being close enough to PC. You agree? So, but theta of P, I mentioned it in the first lecture, it's somehow, it's density of infinite cluster. So if you are above PC, so if you take P, and you look at this probability, theta of P, of course, is probability that origin belongs to infinite cluster, but also another characterization of theta of P could be the following. You take infinite cluster, infinite open cluster, it exists with probability 1 somewhere, and you take a huge box, and you look intersection of infinite cluster with this box. Okay? So, infinite cluster has some edges crossing this box, and if box is large enough, you will have this intersection non-empty. Okay? So, look proportion of edges which belong to infinite open cluster divided by volume of this box, and send size of the box to infinity. So proportion will be exactly theta P. So in other words, theta P is theta P is density of infinite open cluster. So now this problem is open even in dimension 2, where the situation is favorable. So you see, if I choose now P being very close to PC, right? Density proportion of closed vertices, which of open vertices which are on infinite open cluster could be as small as you wish. So apparently, if you give me delta very small, no matter how small it is, it's a proportion with which you are going to open edges in the future. And with which proportion of edges you are going to close if P is very close to PC, is just epsilon. So epsilon could be made as small as you wish comparing to delta. So in step number 2, if you choose P being very close to PC, in principle you can destroy much less edges than you are going to open. So your loss here could be made as small as you wish and compared to delta, except is highly dependent. because you are destroying infinite open cluster. So you are destroying fisherman's net, right? And now suddenly you come with this delta, which now is much bigger than epsilon. So in your universe appear many more edges than you destroyed, right? Except these are appearing in independent manner as Bernoulli new edges, and this was destroyed in a very sophisticated manner. So question is still, can you for every delta positive find P so close to PC that you still recovering these open edges can recover open infinite cluster? This is open in any dimension, including 2, and it's somehow, now maybe we do not have time. If you think over the weekend, we can go back to this problem next week. It deeply, deeply involves structure of critical object. So you need to understand, in fact, pushing this P to PC, how infinite cluster is born. Because you know that below PC you do not have infinite cluster, but large connected components, finite components, somehow are about to be joined into infinite cluster. And at criticality, everything is already nearly ready, and suddenly you increase P by any epsilon you wish, you get infinite cluster, right? And density of this cluster is much smaller now than density delta, which you are going to recuperate. However, what is geometry? That's completely unclear. And in fact, understanding this question, if you can give answer to this, it's also related to large class of models in so-called with very long connections, so-called forest fires models, and relate to existence of many dynamics. Maybe some of you have heard of Altos frozen percolation process, which doesn't exist on certain graphs. So there are very, very peculiar and delicate questions when you introduce long-range dependencies. So this is one of excellent problems to think about. I'm not saying it's easy problem. Okay, so let's finish for today. Maybe I will make some